Hi, welcome to my talk. And my name is Donggang Wang from Cambridge. It's pretty exciting to introduce this recent story I finished with my wonderful collaborator, Guy Pimentel. The title of my talk is called Boostless Cosmological Collider Bootstrap. So our goal here is to find all the possible cosmological collider signals using the bootstrap method. And in particular, we want to identify the large signals and also new shapes that could be interesting for the upcoming observational surveys. So the basic object we are interested in here is the three-point correlation function or the primordial perturbations. If we look up the sky and we could draw some triangles like in the CMB map and also some large-scale structure galaxy distributions, then all these triangles, all these three-point correlators could be traced back to the annual inflation, and they are generated by this three-point correlation function or the primordial curvature perturbation zeta. And this three-point correlator contains a lot of information about the physics during inflation. So what we usually do is to do the Fourier transformation to derive this primordial bispectrum. And in this bispectrum, there are two important parts. The first one is this FNL parameter. Basically, it tells us about the size of this bispectrum and how easy or how hard this signal or non-Gaussianity could be detected. We also have this shape function, and this S is a function of three Fourier mode, K1, K2, K3, and it contains a lot of information that is related to the physics of inflation. And this S function is the focus of this talk, and it's also the major target for future CMB large scale structure and the 21 centimeter observations. The motivation behind it is that we want to detect some new physics and very high energy scales. And the traditional way to do so is to build large particle colliders, and then we could use quantum field theory to study all the possible contributions to this to the collider experiments. There are two Feynman diagrams, two types of interactions that would contribute. The first one is the contact diagram like this with all the external legs. And then we also have this exchange diagram with some intermediate particle. And this could be some new physics in the very high energy. And there should be some imprints in the collider experiments. And normally the colliders could reach the energy scale around 1 TeV also. Then for cosmology, what we are interested in is the cosmological correlators, like the three-point function of the curvature perturbation we discussed before. And there are also two types of Feynman diagrams that will contribute to this to the correlators. The first one is this contact diagram that is due to the self-interaction of the inflaton field. And then we also have this exchange diagram with this intermediate and extra particle in addition to the inflaton. And so through the astronomical observations, we could try to see if there could be some imprints from this exchange new particle, and then we could use cosmology to detect this high energy physics. And the energy scale for inflation could be as high as 10 to 14th GeV, which is much higher than the energy scale of the collider experiments. So this object, this Feynman diagram is the main focus of this talk. And this is basically the idea of the cosmological collider physics, which was first proposed by Nima Cunningham and Juan Medicina back in 2015. And the key insight there is to notice that if we take the squeezed configuration of this momentum triangle, that is to say we set one side of this momentum triangle is much smaller than the other two sides, then this squeezed configuration, it contains information of these extra heavy particles during inflation. And this is a general expression for this squeeze limit. And here we can see that there will be some oscillatory signal. And this frequency of the oscillation tells us about the mass of this extra particle, while this angular dependence tells us about the spin of this exchange new states. And there's a large many possibilities in the literature about the cosmological colliders. Well, in this talk, I will use the cosmological bootstrap method to find all the possible cosmological collider bispectrum. So the cosmological bootstrap is the basic idea is to study correlators from inflation, just focus on the final result and the annual inflation. And Harry Goodhill will give a general introduction about this topic in his talk. So this is a fully model independent approach, and it also gives us one very powerful computational tools, as I will show right now. So in the literature, there are two basic approaches towards cosmological bootstrap. The first one, the theta bootstrap, was proposed by Nima Cunningham, Daniel Baumann, Hayden Lee, and Gabe Pimentel back in 2018. So the basic idea is to look at the theta interactions series with the full de Sitter symmetries. For example, we could look at this massive exchange diagram. And the interaction here is this de Sitter invariant one, this d mu phi square sigma. So in this approach, the de Sitter symmetries are nicely manifested. So basically, we don't need any model dependent input. We just use the Sitter symmetry as a guide, and then we could derive the most general answer with the symmetries. And it's also the first time we could get the full analytical control for this massive exchange diagram. Well, there is also some drawbacks of this approach. The most important one is that in the end of the calculation, we found the non-Gaussianity signal generated in this the theta bootstrap are expected to be very small. And I will explain a bit later that the bispectrum generated here is a zero surprise. And another thing is that in this approach, we always need to compute the 4-point function first before we move into compute the 3-point one. So it's kind of a quite complicated process. And then there's another approach called the Boostless Bootstrap, which was developed by Enrico Paia and also the Cambridge group in the past 2 years. And the basic idea there is to consider series that the Sitter boost is not respected anymore. So there could be some strong boost breaking interactions like this phi dot cubed and also phi dot to the fourth. And so since we have this boost breaking interactions, so large signals for primordial non-Gaussianity are possible. And in the boostless bootstrap, we are able to derive a complete set of cosmological correlators, at least for the single field inflation. Well, the drawback of this approach is that previously it only worked for this massless field interaction. It's not working for the massive exchange like this. So in this talk, I will combine these two different approaches, the Sitter bootstrap and the boostless bootstrap, to propose this new one called Boostless Cosmological Collider Bootstrap. We call it BCCB for short. So here we want to study the large boost breaking interactions with this massive exchange, the particle. And we also want to bootstrap the 3-point function directly without referencing to the 4-point one and then going back to the 3-point. And in the end, we will be able to provide a complete manual possibilities for massive exchange bispectrum. So to be more specific, here we are interested in the inflaton bispectrum generated by this massive exchange diagram with 3 external legs as the inflaton, and that is a massless field phi. And then we also have this exchange massive scalar or spinning particle sigma. So here we wish to include all the possible cubic interaction with boost breaking scenarios, and also all the possible quadratic interaction for both scalar exchange and also spinning exchange. And our approach is to start with this mixed propagator, which is the conversion from the massive scalar field sigma to the inflaton field phi through this phi dot sigma very simple linear mixing interaction. And then using this mixed propagator, we construct this 3-point scalar seed as our building block. So here we include 2 conformally coupled scalar verify and also this mixed propagator from sigma to phi. And here we find this scalar seed can be written as a function of this I hat. And it's a function of this momentum ratio U itself. So it's this momentum ratio is just K3 of this leg. So the moment of this leg, and also K1 and K2 over K3 over K1 plus K2. And then we found this scalar seed satisfies a very simple differential equation with some non-trivial south term. And this is just here we are using this U parameter, this momentum ratio as our variable. And we found this differential equation is just a second order ODE which is only for the de Sitter boundary. And then solving this differential equation, we found analytical solutions. Here is one example of the analytical solution. And here we can see that when this u is much smaller than 1, when u goes to 0, and it corresponds this to the squeezed configuration of the momentum triangle, then we found this oscillatory signal due to the particle productions during inflation. And this basically is the signal of the exchange massive field. And this is the signal of the cosmological colliders. Then the next step we need to do is to generalize this simplest phi dot sigma linear mixing to the most general one for any number of time and spatial derivatives on both phi and sigma field. And our approach is to propose this generalized scalar seed function, this I had with upper index n. Basically, this n parameter is the number of derivatives in this quadratic interaction. And then we found this generalized scalar seed satisfy a differential equation with a higher order South term. And then we can also solve this this generalized scalar seed function using the analytical methods. And then the third step is to do the weight shifting process, that is to map the conformally coupled scalar vary phi to the inflaton field phi. Here we also want to include all the boost breaking cubic interactions for this phi sigma vortex. So we propose this boost breaking version of the weight shifting operator that could map the scalar seed function ahead to the inflaton field, the correlator, 3-point correlator of the inflaton field. And the last step is to do the spin raising process, that is to map the exchange massive scalar to the spinning particle sigma with some spinning index. Here we include this spin raising operator to do this job. And so to summarize here, we in the BCCB, we would be able to derive a complete set of inflationary bispectrum from this massive exchange diagram. So we start from scalar exchange ahead, then we use some two types of weight shifting, two types of differential operators, the spin raising operator to change the spin of this exchange particle, and also the weight shifting operator to map the scalar seeds to the inflaton bispectrum. So in this process, we derive the full shape information of the cosmological colliders. And also we also identify large signals and richer phenomenology in this process, as I will show right now. So let's first look at the size of signal. Why the results from the bootstrap are expected to be small. So if we look at this Feynman diagram of the bootstrap, basically we are taking this one external light to the background in the end of the computation, and this gives us a phi dot. And this corresponds to a mild breaking of the de Sitter boost symmetry. So in this process, we found that the 3-point function of the correlator perturbation as zero surprised is proportional to epsilon. Well, for the boost breaking scenario here, we are considering all the possible diagrams, including these ones with higher derivative interactions, and also various lags being put into the background. Then by summing over all of these diagrams, we found that this diagram then could be derived by the EFT of inflation. So with this boost breaking cubic and quadratic interactions. And this can be seen as the EFT of the cosmological colliders. And here using this framework, we found the size of this, in this framework, the size parameter FNL could be as large as order 10. So it can even be detected using current observations. Then let's look at this shape function and we also just first look at the squeeze limit of the shape function. And in addition to this oscillatory behavior here, in the boost breaking case, we found there are two new things. The first thing is that we have two sound speed. And the CS is the sound speed of the inflaton field, and also we have the sound speed of the massive field, C sigma. Then we also found this phase parameter delta. So for the de Sitter invariant case, this sound speed and also this phase parameter are all fixed by the de Sitter invariant interactions. So this blue curve is the result from the de Sitter bootstrap. And then for the boost breaking case, we found that we still have freedom to shift this phase parameter and also change the sound speed. So for the oscillator signals, it can be there can be more possibilities. One very special case where we found quite interesting is that if the sound speed or the sigma field is much smaller than the sound speed of the inflaton, then the collider oscillatory signals can be shifted outside of the squeeze limit. That is to say, we don't need to go to this u goes to 0 limit to identify the cosmological collider signal. So here, in these two plots, I showed the standard equilateral shape, these blue shapes, and then we propose this new shape called equilateral collider shapes, this orange and also this red curves. And here we can see this oscillatory signal could provide some large deviation from the standard equilateral shapes. And I will stop here, and here is a brief summary of my talk. I will just look forward to more questions in the discussion session. Thanks for watching.